Okay, welcome back. We'll continue with our fleshing out of these ideas of the finite dimensional weak form. In particular, what we're going to do is say a little more about these function spaces from which we are drawing the finite dimensional functions. Okay, so what we're going to do here is talk a little bit, just a little bit, not too much and not at all in a formal way, but hopefully in a rigorous manner. We will talk about function spaces, right? And in particular, the kinds of function spaces we are going to consider are called Hilbert spaces in the branch of mathematics that is usually referred to as functional analysis. Okay, so recall the form in which we specified UH and VH. Right, we said that UH belongs to a space which consists of functions which are drawn from a group of functions that I denoted as H1. And apart from that, we said that UH just needs to satisfy the Dirichlet boundary condition. What we're going to do in this segment is focus upon an introduction to the ideas that are behind these sorts of function spaces, H1. Okay? And in order to do that, let's do the following. Supposing we consider a function u, which actually, let me not use u just to avoid any confusion with either the exact solution or proximate solutions. Let me just say, let's consider a function v. Okay? Consider a function v, which is a mapping from the open interval 0, L to the real space. Okay? And if you recall, when we first started talking about the exact solution u, this is indeed how we wrote it. Okay? So if we have a function v, I will define the following quantity. Okay? I will define the function v to be an L2 function if the following holds. Okay? Supposing we take the function v and we square it. Okay? We square the function and integrate over the domain 0 to L. Okay? Now, if this integral is less than infinity, okay, then we say that v belongs to L2 on the open interval 0, L. Okay? And I realize that what I wrote finally is just sort of restating the first line. So I said define the function v to be an L2 function if that is less than infinity, and then I said then v belongs to L2. Well, same thing. Okay? But essentially what we're saying now is that the function squared integrated over the domain is bounded. Okay? An alternate way of saying it is that the function is square integrable. Okay? V is L2 if it is square integrable. Okay. Now, we're working in 1D, so things are a little easy in 1D. Let's look at what is allowed in L2. Okay. So, examples. Okay. V of x equals to a constant is obviously allowed. V of x equals some polynomial, right? So we could look at it as v of x is equal to sum over k, maybe a sub k, x to the power k, where k is now summed over 0 to n. Okay, this is also allowed. V of x equals h of x minus x naught, where h denotes the Heaviside function. Okay, so h of x minus x naught is the Heaviside function located at x naught. Okay, so this is the right. So this function looks like this. If this is x and this is v, and that is the point x naught, then v is that function, right? Okay, this is also acceptable. And why is that? For each of these functions, you observe that if you square them and integrate them, you will essentially end up with a constant. Okay, you'll end up with a number which is in fact it's a real number. It's therefore bounded. It's less than infinity. So the function is L2. Okay, can you think of a function that is not L2? Right? Think about it. The delta function, right? The Dirac delta function is not L2. So all of these are L2. Okay? If you have the Dirac delta function, v of x equals delta at x minus x naught. Okay? This function does not belong to L2 on 0, L. Okay? Okay? That does not belong to L2. And why does it not belong to L2? For it to belong to L2, you need to be able to square v and integrate it. But the square of a delta function is vacuous, right? It's meaningless. It's not even defined. So the function does not belong in L2. Okay, so these are this gives us some idea of what is implied by L2. Essentially, it is telling us that the function is square integrable. Okay, and it gives us a very basic notion of the boundedness of a function. Importantly, it tells us not just how the function behaves at particular points over its domain, but it gives us an integrated sense of the behavior of the function over the entire domain. Okay, and this is the important property that the integral delivers for us. Okay, in general, one can define LP functions where P is some arbitrary real number actually. Okay, but that gets a lot more complicated and involved. Okay, but let me just state it. One can in general define LP functions. Right, where P itself, well, p could be integers, or actually p could be real numbers. In fact, there even is a definition of an L infinity function. Okay, but we don't need those details for our basic introduction to finite elements. Okay, so that is one type of function that will be of use to us. And you observe that in defining L2 functions, we just talked about the function itself. However, when I introduced the notion of finite dimensional function spaces, and I refer to this space H1, which I'm going to define now, and that step will bring us to the notion of regularity of functions. And the notion of regularity, again, is just a way to talk about how the function behaves with its derivatives. Okay? So let me just pose this question in a very colloquial manner. Okay, so how about control over the derivatives of v? Okay, and this is this whole notion of regularity. Okay, right? And I say control over the functions because now, you know, when we've said so far that the function itself is square integrable, that it's an L2 function, in a sense we're saying that, yeah, the function itself is sort of controlled in some manner, right? It doesn't get too big, for instance, right? It doesn't get unboundedly big. Okay, so we are controlling the function itself, but you haven't said anything about its derivatives. We're going to do that now. Okay, so we say that v of x belongs to H1 on 0, L if integral 0 to L v square plus v comma x the whole square. Now, we need to do something here. As you can imagine, when one gets into physical problems, right, where v would actually mean something with physical significance, like it could be a displacement, it could be a temperature, it could be a charge field or something like that, right, a charge distribution or something like that. When we then take spatial gradients of such functions, we know that we are changing the units of the functions that we're dealing with. Right, the physical units of these functions. So in order to account for that fact and make sure that both terms in this integrand have the same units, for dimensional purposes, we multiply this by L square, where L is just the measure of the domain. Okay? Okay, so we have this, and now we're integrating this integrand over the domain 0 to L. Okay, so v belongs to H1 if the square of the function plus the square of the function's derivatives, okay, or in this case the square of the function's first derivative when integrated over the domain remains bounded. Okay, so let me introduce a remark, and this just paraphrases what I said about introducing L. L has, or L square in this case, has been introduced for dimensional purposes. Right? In general, if you don't want to write L square, or if you don't want to write L, it's common to write m for measure of 0, L. This equals L. Okay? Where m here is the measure of our domain. Okay, in one dimension, the measure of a domain is simply the length. Okay. Well, actually, I need to say, instead of just saying the measure, it's got to be the measure to the power 1 over d, where d is the spatial dimension. Okay. Right. So if we were in 1D, d would be equal to 1. If we were in 3 dimensions, d would be 3, and then the measure would be actually the volume, right? But the volume to the power 1/3 would again give us the notion of a length.